3.9 antiderivatives. So normally we have some type of function, and then we take the derivative, right? So that's usually what we see. So that's derivative. And so, for example, normally f of x is 4x squared minus 3x, say plus 2, and f prime, the derivative would be 8x minus 3, right? We usually take that power, multiply it in front, and then subtract 1 from the exponent. So 1 times negative 3, and then drop that power to 0. That's why it's x to 0. Well, here what we're doing for antiderivatives, it's more of the form would be we go from f to capital F of x. So this one, the f that they would give us would be like the derivative. Oops, got my equal sign, like that. And the antiderivative would be the 4x squared minus 3x, and then we add a c at the end because we can't, when we go backwards, we can't quite figure out what that is. So that is called the general antiderivative. And we take the antiderivative and we add c to it. And then sometimes you will also ask to be able to find c, and so usually you give an equation like that, and then it will say like f of 2 equals 4. So then once you have your antiderivative right here, you'd plug in 2 in for x, or it would be probably capital F, so f of 2. So you plug in 2 in for x, plug in 4 in for capital F, and then solve for c and enter that back in. So here's a quick examples that you can do. So here, if this is f, which would be, in our spot, this is the derivative. So these would be derivatives. And we're trying to find capital F. So what you notice is what's happening is we're just going backwards. So instead of multiplying, we're going to be dividing. And then instead of subtracting 1 from the exponent, we're going to be adding 1 to the exponent. And so what you'll see is on our original, this is exponent of 1. It comes to an exponent of 2. And how do I go from 8 to 4? Well, by dividing. And what do I have to divide 8 by? We have to divide by 2. And you can see that 2 is right here as an exponent. So just like we times our exponent in front, we're going to divide by our exponent. So here, we're going to add 1 to our exponent, and then that's what we're going to divide the coefficient by. So 1 divided by 4. And then we're just going to add 1 to the exponent. The exponent here is actually 0, so it'll become 7 to the first, and that's the exponent that we're going to divide by 1. And so that one we could just leave off. So the antiderivative is 1/4 x to the 4th. And we can always check these ones too by just taking the derivative of them. So this one we're going to add 1 and then divide by that number. So divide by 4, add 1, divide by that number is 4. So the antiderivative is 1/4 x to the 4th plus 3x. And then this one we add 1, and then divide by that. So we're divided by 4. So we can see that one is 1/4 again, x to the 4th plus pi x. Right, because pi is just really a constant. It's just a number as well. So there's some examples for you. So general antiderivatives. So here's our our derivative, and we want to find the antiderivative. So we're going back to our original. So we're just going to add 1 to that exponent, and then that's what we're going to divide by. Okay, and then we just add c at the end. So that's the kind of formula or equation or whatever you want to say for the antiderivative. And then so here's an example. Basically come through, add 1 to all the exponents. So this would be an x to the 0. So I'm adding 1 to that. And this is already 1, so I'm adding 1 to that. And then that's the number, that new exponent's what I'm going to divide by. So I'm going to divide by 4, I'm going to divide by 3, divide by 2, and divide by 1. And then I'm just going to add a c at the end. So this is 1/4 x to the 4th. And again, you can just take the derivative of this one, and that will get you, to the red one there. That's how you can check your work. And then this one will just be x, and then plus c. Okay, here's another example. You can try this, you can try this on your own, or maybe I'll rewrite it for you first, and then you can try it. So here we don't want to do quotient rule or anything like that, because we can't do quotient rule. So we want to rewrite it as a polynomial. So I can rewrite it, just put the x cubed underneath each of them, and then simplify, bringing the exponents to the top. So f of x is equal to 3x plus 2x to the negative 2. And then we can add 1, and divide by that number. So our antiderivative, and again, you can check your work by just taking the derivative. That'd be a negative 2x to the negative 1. And then we could even rewrite that. F of x, equals 3/2 x squared. And this would just be minus 2 over x, like that, because it's a negative exponent. And then you just add c at the end. Okay, more finding the value of c. So we take the derivative. You can try this one on your own, and I'll help you find c. Add 1, divide by that new exponent. Add 1, divide by that exponent. Simplify. Right, again, you can check it. Add c. So now here it wants us to find the value of c. So f of 0, that means this is 0. Or sorry, f of 0 means my x is 0. And the capital F of x is going to equal to 1, because that's my y value. And now I can simplify and solve for c. So c equals 1. And now I can come back and just plug in that one right there. And so there's my exact answer. Okay, here's another example you can try on your own. So you can pause it and get to it. You can rewrite this as a half power, then multiply these. This would be a 2 over 2, so that'd be 3/2. Now go ahead and you can try this one. So here you're going to add 1 to this, which is same as adding 2 over 2, so which is 5/2 as the new exponent. And then I'm going to divide that by 5/2, which is the same as multiplying by 2 over 5. So this becomes, let's put an equal sign in here, 2/5 x to the 5/2. And we can see if we multiply that, that would cancel out, right, to a 1, that's what I'm starting with here, is a 1 in front. And if I subtract 1, which would be 2 over 2, would be 3/2. And then we can add our c. And then we give a capital F of 1 equals 2. So this is 2. Our x is 1, which is really nice when we raise a fraction to a power. Well, when we have a number raised to a fraction, if it's 1, it's really great, because then it just becomes 1. So really this is, that's a 5, sorry. So really this is just going to be 2/5 equals 2 plus c. So subtract 2/5. And 2 is the same as 10 over 5. Subtract that, that's 8/5. So c is equal to 8/5. So then we can come back. This is 2/5 x to the 5/2 plus c, and our c is 8/5. So there we go, there's the antiderivative. Okay, so this is useful in finding the position function. So going backwards, so if we're given the acceleration like we are here, we can go backwards and find the velocity, and then from the velocity we can go back and find the position function. So it's just kind of going backwards from what we've already done before. So we have particle moving forward, straight line, acceleration. Here we have our equation, and then we have velocity. And then we're going to go ahead and find our initial position. And so what these two pieces of information give us is help us to find that c value. So this is actually 0. So that would be my x, and this would be my y. This would be my x of 0. This would be my y of 9. So I'm going to take this equation. So this is like the derivative. And velocity would be the antiderivative. So add 1 and divide by that. So I'm going to add 1 to my exponent. My exponent currently is 1, so I'm going to add 1, divide by that. So 3t squared plus 4t. So that's the antiderivative. And then we go ahead and plug in 0 in for our t, because we got to find our c, add c at the end. So that's going to be 0. That's going to be 0. So really you just get c equals 6, because v of 0 equaled, oh, negative 6, sorry. Negative 6. So negative 6. So now we can enter that in. So our velocity equation, which is the antiderivative acceleration, is 3t squared plus 4t plus a negative 6, which is just minus 6. Now I can take the antiderivative of that, which is our position function. So that'd be adding 1 to the exponent and dividing by that. So 3 over 3 plus 4t squared over 2, and then minus 6t. So that's just t cubed plus 2t squared minus 6t. And then again, we can go add c at the end of that. And then that's why they give us s of 0 equals 9. So plugging in 0, 0, 0, 0, that's going to get 0, so that's just c, and then it equals to 9. So c equals 9, so our position function is t cubed plus 2t squared minus 6t plus 9. And there's our position function. All right, so the last part is go ahead and graphing the antiderivative. So that's capital F of x. And then we're given this spot 0, 2. So here we're giving this right here, this blue one, is our derivative f of x. Okay, so we gotta think about this backwards a little bit, because remember, on the derivative, this is f, this would be our slope, and x is just represented by our x's. But when we go backwards, this y-axis is not our slope, it's just our normal y's, and the x's are still just our normal x's. So before we graph the derivative, right, these are where we had hills and valleys. So we're going to have hills and valleys at that. So we kind of got to look at it as kind of backwards. So here, as we are below the x-axis, that means we have a negative slope. So I'm just going to put negative m. And here above, we have a positive slope. So here, that means that we would be decreasing until we get to this valley of some sort right at this point. So we're decreasing, and then we're above. So that means my graph is going to be here, these same x's. Sometimes it's best to graph this on the same one. So I'll say this x is 1, 2, 3, 4, and 5, okay? So 1, 2, 3, 4, and 5. So at this point right here, let me use a different color. That's still the same color. This point, I'm going to valley. So I'm negative here, so that means I'm decreasing to some point. It doesn't really matter above or below, it doesn't really matter here. So I'm decreasing up until that point of 1, and then I'm positive, I'm above the x-axis, so that means I'm increasing in my graph. And then here, there's special time for this. We'll talk about that. And then over here at 3, I'm going to have another hill or valley, right? So at 3, I'm going to have another hill or valley, right? And because I'm above, that means I'm still increasing, right? Because I'm above the x-axis here, I am still increasing. So that's why this graph is still increasing here. And then at this point 3, I reach its max because I have a 0. And then I'm below, my graph is below, so that means I'm decreasing. So from this, I am now decreasing. So I'm going down at 4. And then at 4, it kind of has a little max or min right there too of our derivative, right? So that means something's happening here at 2 and something's happening here at 4, but it's not a derivative. And then as we can see, we get closer and closer to a slope of 0, right? So that means my antiderivative, when my slope is getting closer and closer to 0, my antiderivative would be getting closer and closer to a flat line, to a horizontal line. So that means we're evening out, but we are negative. So normally the antiderivative would be here, would be negative, right? Going down, decreasing. But here we are decreasing because we're negative, but it's flattening out. So we're getting closer and closer and closer to a straight line, but we're still going negative, right? Still negative, where this would be positive slope. So what we're doing is getting closer and closer to a flat line right here. So that's what the antiderivative might look like. Again, you can move that up and down based on what C is. And so that's why I give you this piece of information right here. So our graph should look something like that, our antiderivative. And then this last piece right here is going to help us narrow this down, because it says we have a point on this antiderivative of 0, 2. 0, 2. I'll just go ahead and let that be 0, 2. And so that's how you graph the antiderivative. So we'll talk about it in class.